Hello, welcome to a video on pages 3 through 5 of the section 5.4 notes regarding the fundamental theorem of calculus. So before we begin page 3, let's recap example 2 on page 2 of these notes. So on example 2, we were looking at the function y equals t minus 1, and we defined a of x, or the area between t minus 1 and the x-axis, to be the integral from 1 to x of t minus 1 times dt. And when we went through this example, we noticed that the area can be expressed as a function of x, and more specifically, it seemed as if the area function was quadratic. There was a low point at 1, 0, a sense of symmetry with x equals 0 and x equals 2, and x equals negative 1, x equals 3. And when we went a bit deeper, and if we look at the yellow region, where we're starting at x equals 1 and going towards some arbitrary x coordinate off to the right, the length of the base is x minus 1, simply the difference in x coordinates. For the height, that would be also x minus 1, because we're considering the x coordinate over here just be x, so the x coordinate over here is also x. Plugged into t minus 1, the y coordinate is x minus 1. The y coordinate represents the height of that triangle. Since the y coordinate of this point down below is 0, so the height's also x minus 1. So area of a triangle, it's right triangle, 1/2 times x minus 1 times x minus 1. That's what a of x is going to be. And if we were to FOIL it, of course, we get half x squared minus x plus half, and distribute the half as well. So now we'll go to page 3 of the notes, and we can deduce that the integral from 1 to x of t minus 1 times dt, which is of course our area function, is just going to be half x squared minus x plus half. The right-hand side of that equation is going to be the antiderivative of x minus 1. And if we were to take the derivative of half x squared minus x plus half, we would get 1/2 times 2x minus 1 plus 0, or x minus 1. So this tells us that the derivative of our definite integral with respect to x from 1 to x of t minus 1 times dt is just x minus 1. And it's not a coincidence, because in general, if you ever take the derivative of a definite integral with respect to x, where your lower limit can be any constant, and we'll talk about that in some of the examples, why that could be any constant, and your upper limit is just x, and you're taking the integral of f of t with, of course, respect to t, you're just going to get f of x. So the derivative of your definite integral from 1 to x of f of t times dt is f of x. It's almost like the derivative and the definite integral kind of cancel out, and you replace the t with x. That's kind of what's happening here. And that's the fundamental theorem of calculus part 1. So if we define it a bit more formally here, if your function is continuous on a to b, capital F of x, which is an antiderivative of little f, so then that could be defined as the definite integral from a to x of f of t times dt. You'll definitely have a derivative at every point x in your interval, closed interval from a to b. So therefore, d of capital F of over dx, which is of course the derivative of your antiderivative, or we can write it like this: d dx, the integral from a to x of f of t times dt. That's just going to be f of x. So that's kind of the key concept here, is that the derivative of an antiderivative provides the original function. One way you could put it in words. And that's the fundamental theorem of calculus that is pretty important, because we want to be able to realize that there is an inverse operation to derivatives, that being an antiderivative, and kind of prove that. So there's some implications behind this. Since we did say that our original function is a derivative of the antiderivative, then every continuous function will be a derivative of some other function. Some of these implications are a bit abstract, so it might take a while to kind of sink in. But again, if you have a nice continuous function, apparently this function here is a derivative of some other function. Also, every continuous function has an antiderivative, meaning that you can basically think of a function, take derivative of it, and that will get you back to the original function, because the derivative of the antiderivative gets you back to the original function. The antiderivative will also be continuous on your interval from A to B, closed. And since FTC says that df over dx, d capital F over dx exists everywhere on the closed interval from A to B. Also, because our function is differentiable, it must be continuous. We did talk about that. Those that are not continuous are not differentiable. The contrapositive would be true because there's no way I can find a derivative of a discontinuous function, because the way we define the derivative is that you take 2 points that are very close to some x-coordinate, you draw a secant line, but then ultimately you get those 2 points closer together, so it becomes a tangent line. The slope of that tangent would be a derivative. It can't happen for non-continuous functions or discontinuous functions. So differentiability leads to continuity. No continuity means no differentiability. The process of integration and differentiation are inverse operations. And also very important that we realize that if I have, like, say, y equals x squared plus a constant, my derivative, of course, is 2x. If I take the integral of 2x with respect to x, so I take the antiderivative basically, I get back to x squared plus c. So it kind of comes full circle. And that's really kind of the main essence of FTC Part 1. Before we do some examples, it is imperative that we have a discussion about the operator d over dx. So you don't want to confuse d over dx with dy over dx. See, this right here simply means take the derivative of tangent x, that's all, which you know is secant squared x. So it's an operation. But this right here, there's actually be a multiplication in between, means to multiply the derivative of y with tan x. So in that case, it's secant squared x times tan x. There's no multiplication for d over dx of tan x because that's an operation. So just don't confuse those two things, because we do want to exhibit notational fluency. It's very important for this stuff and not get things confused. The College Board is very heavy about that when it comes to the AP exam for Calculus AB. So you want to make sure you're comfortable with the notations. Okay, if we move on to the next page, we'll talk about some examples. Before I do example 1, let's consider this definite integral. And let's take the antiderivative out, which hopefully you know is t cubed over 3 plus c. And our limits are 1 to x. So this is the notation we tend to use for showing that we're doing the definite integral. Of course, I plug in x first, that's our upper limit. Plug in 1 after that, that's our lower limit. The constants cancel, so you get x cubed over 3 minus 1/3. Okay, great. But what if I also want to do the derivative of all of my work here? Well, we realize that when I take the derivative of x cubed over 3 minus 1/3, that's 3x squared over 3 minus 0, which of course is x squared. So it's interesting to note that we had t squared as our integrand, and when I did the definite integral and then the derivative afterwards, it's basically the same thing, just x squared. This right here, all this is basically FTC part 1. And that's what we're going to basically utilize for our examples on page 4 and 5. And remember, FTC part 1 is just saying this: d dx of some constant is your lower limit, x is your upper limit, f of t times dt equals fx. Now, I did say earlier in our notes that our lower limit can really be any constant. And if we think about it, what if I change that to a 2? Okay, fine. Now I have 2 cubed over 8/3. But then when I take the derivative, I still get the same result. So it doesn't matter what the lower limit is. It could be anything. So that is kind of a nice segue to example 1, because here we see a 0 and negative pi over 4. Everything else is the same. You're asked to take the derivative of this definite integral. So these are different, but it won't matter what constant lower limit is. It won't matter at all. So in this case, we just get sine x for both of them. As long as everything else fits well with FTC part 1, the constant in the bottom could be anything. So example 2 kind of shows that again. By the way, don't find the antiderivative of the integrand. Remember, the integrand is the expression that you're taking the definite integral of, which you ultimately do the antiderivative, and then you plug in your upper and lower limits, take the difference, and you're done. Don't do that here, because the question is asking you for the derivative of the definite integral. So, and you're also being asked to use FTC. FTC part 1 is right here. You're just going to replace t with x. As long as your constant, as long as your lower limit's a constant and your upper limit's x, then guess what? That's interesting. It says anti-double. Look, that's weird. Yeah, I guess you could think of, well, anyway, I'll stop there. But yeah, kind of funny how it says anti-double. So yeah, it's just going to be 5 over, so dy over dx is just 5 over 3 plus x squared. Our upper limit was just x, our lower limit was a constant, and I'm just taking the derivative of both sides with respect to x, So yeah, there we go. Now example 3, we do see a slight problem. The upper limit is now a constant, not the lower limit. So the upper limit's a constant. If I were to reverse the upper lower limits here for this example I kind of made up a little earlier, then of course you're going to have this. You don't even have to really write this down, just kind of just watch this part. I'll copy it later. But then it's just going to be 0 minus 3x squared over 3, or negative x squared, which, is different in sign. So what I'll do is I'll use one of the properties talked about in section 5.3. When you reverse the limits of integration, you change the sign. And of course, now when I do my derivative, it's going to be negative secant x. So not too big of a deal when it's reversed. Just got to keep in mind that you just change the sign of your result. Now what if the upper limit is not plain old x? It's something else. Now, let's go back over here again. I'll make that 2, again, the lower limit, but x squared. So I have to change everything else here. So now that becomes x to the 6. It's still 8/3. So now when I take my derivative of this, that's going to be 6x to the 5th over 3 minus 0, which is 2x to the 5th. Now here's where it gets a little interesting. You know, before, we were just playing with x, we replaced t with x, call it a day. I can kind of try to do the same thing. I'll do some blue. You know, if I replace the t here with x squared, then I just have x to the 4 power. But if I multiply by derivative of x squared, oh, look at that. I get 2x to the 5th. So it's kind of like a chain rule situation. So I can replace t with the upper limit, and of course work out the expression, and multiply the derivative of the upper limit. And I got the same thing. So for example, 4 dy over dx can be thought of like this: tangent of 5x cubed squared, so we're replacing t with the upper limit, minus 3 times 5x cubed, and of course times the derivative of 5x cubed. It's a bit of a chain rule here. So it's just a tangent of 25x6 minus 15x cubed times 15x squared. And that would be the answer for that one. So you can use chain rule. As long as your upper limit is a function of x, so that's a function of x, then you simply just find the composite function f of g of x times g prime x. And really we have been doing that for all the other ones. When x is the upper limit, but what's the derivative of x? 1. So you don't show it, but it's almost like we're doing the same thing. We got to be a little more deliberate about it when the upper limit's not just plain x, it's something else. And of course, make sure your lower limit is a constant. And again, the lower limit could be any constant, as we've shown already with some of these other problems here. Okay, let's step this up a bit more. For example 5, notice how our limits are 5x and x squared. So we do have another problem. Neither limit is a constant. So I'll have to get a bit creative or resourceful here, as we see. What if I picked a constant that's in between 5x and x, we're going to call it a. Okay, so a is between 5x and x squared. So we're going to partition our interval, meaning that we can rewrite our integral, our definite integral, in this way. And we're using another property that we discussed in 5.3. So everything kind of builds upon itself, as you can tell, this course. We're using, actually, right up here. You might remember the additivity property. From section 5.3. And that totally is fine because the upper limit of your first integral is equal to the lower limit of the second integral. So they link up, it's a contiguous region, it's not a problem. So of course, you say y equals this reverse limits of integration so that the constant is now, the lower limit is now a constant. I'm getting lazy, I'm not going to rewrite that second integral. But then when I do take a definite integral, that's going to be negative sine 3 times 5x, going to replace t with 5x, my upper limit. Do a chain rule, so it's just times 5, plus sine of 3 times x squared, do a chain rule, times 2x. This is something that you tend to see often on the AP exam, so you really want to know this. Okay, last example, then the video will be over. Example 6, you're asked to find a function y such that the derivative of our function is that, and of course when x equals -5, y is 7. Here's the problem. So you want to find the antiderivative of sine squared. So you have to think of a function, or sorry, sine squared x. You have to think of a function where if you took the derivative of it, then you would get sine squared x. Because remember, the derivative, the antiderivative gets you back to the original function. That's tricky. See, what if your derivative was sine x? Then the antiderivative is negative cos x. Because the derivative of negative cos x is sine x. But the derivative of something is going to have to equal sine squared x. Jeez, that's a really tough one. So finding the antiderivative analytically is tricky. Guess and check won't work as easily. It worked fine for, again, y equals sine x. Sorry, dy over dx equals sine x. Then y would be negative cos x. And we probably would have to resort to some trig identity, which we really don't do in this course or on the AP exam, so we're not going to really go there with that. So we need to be resourceful again. And here's what we're going to do. Really, your answer is that. I'll say it's almost the answer. But if you think about it, it's using FTC, right? d dx of your integral from a to x of f of t times dt equals f of x. At where y is f of x, right? And we want to know what f of x is. So really, we could just think here for a sec that if y equals some integral that we see right there, then the derivative of that integral will actually get us what we're looking for. So d dx from a to x of sine squared t times dt plus k. See, if I took the derivative of all that, I would get sine squared x using FTC plus 0, or just sine squared x. That's k, sorry about that. So yeah, that's basically what is happening here. Is that we can just write y as a definite integral. Now FTC does say something a little different, that the derivative of the definite integral is y. We're saying y is a definite integral, so it's a little strange, a little weird. But that's because we're told that our derivative is sine squared x. We want to find what the antiderivative of that is. So we just write as a definite integral. But as I said, we almost have our answer because we have to also satisfy these initial conditions. When x equals -5, so f of -5 equals 7. So here's what we're going to do. If I let a, my lower limit constant, be -5 and k be 7, then y is a definite integral from -5 to x of sine squared t times dt plus 7. The reason why that works is because if I do plug in -5 in for x, that integral becomes 0 because your lower and upper limits are the same, leaving with y equals 7. Plus, if I take the derivative of that using FTC, the derivative of the definite integral kind of cancel out. Got sine squared x, and the derivative of 7 is 0, so dy over dx would be sine squared x. There's a bit of graphing that will happen here. We could talk about that later because I didn't quite do that with the previous classes today. So that pretty much concludes the video. Come by if you have any questions. and give your homework the best shot. You should be able to do the homework just fine because the examples here are like the homework. So yeah, looks like we're all set. All right, see you guys later.